Alright, good morning. I am not available today. I had to be at a meeting, so I'm creating this video. I want y'all to go through this video. I will go through everything step by step. I want you to follow along on the worksheet that you have in front of you. So that way, hopefully this will help you explain. I want y'all to work in groups, share iPads, share video presentations, however this works. Monday, we will try to go over this some more, problem for problem. And if that means we move the test a day or two, that's fine. So just keep that in mind. We will definitely try to go over this some more, but you need to start trying to do some of this on your own. So today we're talking about linear programming. It should be found on page 205 in your book. Linear programming is, these are some of the vocabulary terms that you're seeing right there. Linear programming is a method used by business and government to help manage resources and time. The constraints, we use constraints with linear programming. These are conditions that limit the available resources and represented by inequalities, because not every business can just say, I'm going to make a ton of these products and be able to make tons of money like that. There's always something that kind of restrains them from being able to always make a bunch, and also available resources, and also what prices they can charge to make money. Real world constraints you always will have. Keep in mind, you will always have x is greater than 0 and y is greater than or equal to 0. So keep that in mind. This will always be part of your constraints, those two equations, a horizontal and a vertical line. Feasible region. This is the intersection of the graphs of a system of constraints that includes all the possible solutions. Okay, so you can see in example 2, there's a graph there with a shaded, cross-shaded area. That's a feasible region. The objective function. This is an equation representing quantities such as revenue, profit, or cost used in business to determine how to make maximum profit with minimum cost. The idea here is this. We're going to take a word problem. We're going to, based on some sentences, create some inequalities that will create our feasible region. Then we will use an objective function, whether we want to minimize costs or maximize profit, to figure out where it would be best for that business to, say, meet what we're trying to do. And then they tell you about how the vertices are where there will always be maximum or minimum value. So what we're doing here, when we're looking at our feasible region, we will look at only the vertices. Anything else is a possibility, it could work, but does not give you the maximum potential, or in terms of cost, the minimum cost. So let's look at example 1 using the given restraints, and I know it does look a little blurry. Follow along on your worksheet. Graph the feasible region and identify the corner points. So x greater than or equal to 0 is a vertical line. So a vertical line that goes straight up and down. That's x greater than or equal to 0. I won't graph the shaded part of that yet. Y is greater than or equal to 0 is a horizontal line. And then 3x plus 4y equals 12. I'll go ahead and use the intercept method, which would say, what's 12 divided by 3? 12 divided by 3 is 4. 1, 2, 3, 4. Let me go ahead and do that one in red so you can kind of see that. 1, 2, 3, 4. Okay, and then 12 divided by 4 is 3. 1, 2, 3. That's my y-intercept. So if I graph this, connect those two dots, I've got this. Now, my feasible region ends up being right in between. So this little section right here, that's my feasible region. Kind of hard to see. Probably should try, let's try like a little bit. That right there is my feasible region. Okay. Now, what they also want you to identify is you've got vertices, corners. These 3 corners at 3 or 0, 3, that's this one right here, 4, 0, that's that one right there, and then 0, 0, that's at the origin. Those are our corner points, and those become important later. Okay, that's all you have to do for example number 1. So example number 1 was trying to prepare us to see how we make the graphs and how do we do the shading. Notice how the shading was kind of in the middle. Example number 2, we already have a graph done, and you can kind of see the different points, although it's very hard to see. Find the minimum cost or maximum profit for the feasible region shown below. Okay, so these right here are objective functions. And with the objective functions, what we're trying to do is we're trying to see which one gives us the most, or like can give us the most or the least. When it's a profit, we want the biggest answer. When it's cost, we want the smallest answer. Okay, because cost, we want to minimize our cost, and profit, we want the most profit. So, what do we do here? Okay, you've done these graphs, you've identified your corner points, and you go, well, how do I find the maximum profit? Now, maximum profit usually should be, it's going to be at one of these higher points. Maybe even the 6-0, but I don't think so. So I'll try those points first. So let's see and do 2 times 9 using this point right here, 9 comma 4, and I know this is blurry. Look at your worksheet. 2 times 9 plus 5 times 4. And when I do that, I've got 2 times 9 is 18, 5 plus 4 is 20, so that equals 38. And then I try the higher point. 2 times 4 plus 5 times 8. 2 times 4 is 8, and 5 times 8 is 40, and so 40 plus 8 is 48. Okay, if I try the 6 comma 0, 2 times 6 plus 5 times 0, it's only going to give me 12. Now I can kind of tell because the y has the bigger answer, or the bigger number that's going to be multiplying. So the bigger the y, the more profit I can make. So that's why 4.8 was better than 9.4, partially. But you still should still check it out. So we can see here that our maximum profit happens at 4.8. So that was our maximum profit, 4.8. Now for minimum cost, I would want something that would be at a lower point. So again, maybe I look at this 6.0, but then I also look at these 2 points. And if you look at it and if you use a little bit of common sense, you should recognize that this point right here, 2.2, is probably going to be a little bit lower point than the 2.5 because they both have the same x, but one had this point, this higher point right here, 2.5, has a higher y than the other one. So more than likely I would just test these two because they're the lower ones, but I'll show you even with the 2.5. Okay, so we're looking at 5x plus 2y, and we want to see which one of those is going to give me the least amount. So 5 times, because this is the cost, we want the smallest number. 5 times 2 plus 2 times 2 is 10 plus 4, or yeah, 10 plus 4 is 14. If I do 5 times 6 plus 2 times 0, I've got still 30. And if I do 5 times 2 plus 2 times 5, that gives me 20. So you can see here the smallest one was at 2.2. So this one, 2.2, represents the point of least cost. So depending on what the question is asking, you may want to analyze whether it's the least cost or whether it's the maximum profit. Okay, so this gets us to our first full real example. Company ABC makes 2 models of door handles, plain and decorative. Okay, let's think of that as our X and our Y. Each of which must be assembled and packaged. The plain handle requires 12 minutes to assemble and 2 minutes to package, while the decorative handle requires 18 minutes to assemble but only 1 minute to package. Each week there are 240 available hours for assembly time and 20 available hours for packaging. If the plain handle sells for $2.20 and decorative handles sell for $3.50, how many of each type should be made to obtain maximum weekly income? What is the maximum weekly income? Okay, so if I decide to say that the X is the plain and the Y is the decorative, I need to also look at this problem a little bit better. So we know we can see here, according to this, we have 12 minutes to assemble a problem, or to assemble a plain handle. Also 2 minutes to package. But notice, assembling and package, this is kind of like two different things. Here I have 18 minutes to assemble for the decorative ones, but only 1 minute to package. And then overall, each week, I have 240 hours for assembly time and 20 hours for packaging. So obviously we're talking about hours and minutes, so you might need to change those hours to minutes. And then we're talking about money. Now money usually goes with profit, and profit and cost become our objective. So to write the constraints for this problem, again, first off, we're saying X has to be greater than or equal to 0. Okay, so I have to have some handles. I have to have some plain ones. Y has to be greater than or equal to 0. I have to have some decorative handles. Now, if you look at this and think of these, we want to put these things together. I've got assemble, assemble, assemble. That probably works together because I'm talking about total assembly time for both sets of handles. So I can say one of my constraints is 12x. Notice how I put 12 minutes for the assembly time of a plain handle plus 18y. I cannot exceed 240 hours, so I need to be less than or equal to 240 times 60, which would be 0, 0, 24, carry the 2, 14,400. Okay, I changed the 240 hours to minutes. Okay, another constraint is I have 2 minutes for packaging for the plain plus 1 minute for the decorative, and I have 20 available hours for packaging. 20 times 60 is 0, 0, 1,200 minutes. Okay, so I converted all of this to minutes. Now to graph, so basically I'm looking at 4 lines. And those will be my lines to help me figure out my constraints. And I'll show you what we mean. So the next thing we want to do is graph our constraints. Really, to graph these constraints, I probably need to know the x and y intercepts. So on this first one, it would be helpful to see the x and y intercept. 14,440 divided by 12 is... Okay, so when I do 14,400 divided by 12, doing my x and y intercepts, because this would be a lot easier with x and y intercepts, I will get, my x-intercept will be 1,200. 1,200. My y-intercept will be 800. Okay, then for this one, if I divide 1,200 divided by 2, obviously the x-intercept is 600. I'll write that one down here. Then 1,200 divided by 1 is 1,200. Okay, again, notice I'm just using x and y intercepts. So I need to graph this. And when I do that, these are very small lines, and obviously you can see this is kind of squeezing it. But I'm going to have, so I would probably say something like this. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16. I think there's like 18 like lines here. If I divided this to where I could do, each one of these is like 100. 100, 200, 300, 400, 500, 600, 700, 800, 900, 1,000, 1,100, 1,200. There's 1,200. So I'm saying that's 1,200. Okay, do the same thing over here. This is 800. 1, 2, 3, 4, 5, 6, 7, 8. Okay, there's that line. It's a solid line because I can be less than or equal to. Okay, so I've graphed that line. This one is 600 for the X. 1, 2, 3, 4, 5, 6. I'm going to do that one in a different color. 1, 2, 3, 4, 5, 6. And then 1200 for the Y. Okay, so again, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, connect that. And again, the straighter you can make this line, the better, because that way this will help you see that intersection point. So a ruler can kind of be very handy here. Let me try for the other one a little bit straighter. Okay, you can kind of see my line was a little bit off. So that I can see that there's an intersection point right here. Okay, and that point, it would appear, is at 1, 2, 3, 300, 1, 2, 3, 4, 5, 6. That point is at 300, 600. Okay, and I noticed I also didn't graph my x equals my vertical line at x greater than or equal to 0, and my horizontal line y greater than or equal to 0. Okay, when I do that, I also create a vertices here, I create a vertice here, I create a vertice here. I've got places where these are crossing. Now, if you look, these are greater than, greater than, greater than, less than for the diagonals, less than, less than. That means that my graph is, this is my feasible region right in here. So I have these points. Find the vertices of the feasible region. Well, I've got the point 300, 600. I've got the point 800, 0, or 0, 800. 0, 800 is this point right here. I've got this point right here, which is at 1, 2, 3, 600, 0. 600, 0. And then I have 0, 0. This point right here. Okay. They all lie around the edge of the shaded area. This is where there would be cross-shaded. So we need to use those points with an objective function. Well, what's the objective function? The objective function is take the dollar amounts. I make 220 for the plane handles. So the profit is made 220 times the plane handles, which is, we said, is x, plus 350 y for the decorative handles. And to figure out which one is the maximum profit, you just need to plug in those numbers and see which one gives you the max amount. So you're saying, like, what's 220 times 300 plus 350 times 600? Is that going to be a bigger amount than 220 times 0 plus 350 times 800? And is that going to be a bigger amount than 220 times 600 plus 350 times 0? Well, 220 times 600 is going to be less than 350 times 800. So I really only need to test these two. And when I type those into the calculator and come up with an answer, I get 2,760 for this one, for the top one, but I get 2,800 for the 0,800. So that tells me this point right here, 0,800, is where I would make my maximum profit. What does that mean? It means, honestly, for this company, making plane handles does not make them the most profit. If they made nothing but decorative handles, spent their entire week making 800 decorative handles and no plane handles, they would make more money than the other way, than if they made some plain handles and not quite as many decorative handles. But obviously, realize this, anything on this feasible region, anything in that purple section, or even this 300, 600, means the company makes money. The question is it best for them to try to go for that maximum profit, or do they go for something a little bit less? That's basically what you have to do here. I will try to do another example. I will save a video for that for later. But see if you can follow along. See if you can figure out how to. Go through the next problems. See if you can read the problem, figure out the constraints, figure out what's your x and your y. Do these, follow these steps, find your vertices, and find your objective function. If you can at least handle A and B and D, most of this will get easier. Okay. If you do have any questions, feel free to ask. I will try to post up another video of just one other example later on, because this one is getting kind of long. But I would like you to try to do is the guided practice, the Farmer Brown question, and the next one, the independent practice, Sasha question on your own, or with a partner. Work with some members in your group, in your class, and see if y'all can do this. We will go over this again on Monday. And I, again, want you focused to working on this, because you're going to have to make sure that you do understand this. This will appear on the test. Thank you for your time. I hope this was informative, and we'll go over it again some more on Monday.